This is a little bit different. I kind of feel like I'm on a Sunday morning talk show here, just going to ask the hard questions about our guests here. So let's bring them up. Professor Conde and Kylee, come on up. So what we're going to do tonight is we've got a lot of questions to ask about space weather, of course. And I'm going to run through them. There's a lot to learn. And then at the end, of course, we'll have your questions from in the audience here and our online crowd. Hello, online crowd. Okay, all right. We all pay attention to the weather, all right, that's here on Earth, how it affects us. We need to know how to dress going outside. In Fairbanks especially, we like to know if it's going to be 40 below. I imagine our online crowd, they pay attention to their weather as well. But so we know a lot about weather around us, but I don't know how much we all know about weather going on way up there, and it's kind of odd to consider it weather. But so we're going to learn all about that. And before we actually get into the nuts and bolts of science weather, we're going to find out a little bit more about our two guests tonight, and we'll start with Mark. You've been, you're a space physicist, so how long have you been doing that, and what got you interested in the field?
Well, thanks, Rod. And can everyone hear me? Yep. So I got started in this field in about, 1983, when I started as a graduate student in Australia at the University of Adelaide. And, you know, I think the honest answer to why I got interested in space physics was I grew up in an era when the US was embarking on the Apollo program to go to the moon, and it was an exciting time, and there was all sorts of technology involved. And that's a perfectly fine answer to your question. There's also a slightly embarrassing answer, but I don't know if I should share that with you.
Yeah, I think you should, because I don't know it, so I want to know it.
He doesn't know this. So I was, I was a fourth-year student at the University of Tasmania in Australia, and we had a student study room that was in our department, and the room just happened to be near the entrance to the department there. And outside the door of our study room, I saw a notice on the board one day that said, opportunities for graduate students to pursue research topics in Antarctica. And I thought, oh, that'd be great. I really want to go to Antarctica. So that's part of the reason that I ended up in this field. But also, because of where our office was, all the visitors to the department would come in, and the first place they would come to was us when they wanted directions for where to go. And we figured it out, and after a while we'd get a bit sick of this, and being young students, we were a bit mischievous, and after a while we'd start sending them off on wild goose chases to weird places in the building. And one Friday afternoon, someone came and asked for directions for somewhere, and I sent them off to the second floor women's bathroom way down the end of the building somewhere. And then 30 minutes later, another person came and asked for directions, and I was wanting to speak to one of the members of the department. I was feeling really guilty and bad about having messed the previous guy up. So this time I was really polite, and I took the person up and walked him up to the third floor and found the office of the professor he wanted to talk to and introduced him, and went back downstairs. And about 10 minutes later, this guy came down and said, well, I actually came here to speak to you because I'm the director of the Institute for Antarctic Research in Adelaide, and you've applied to my institute to be a graduate student, so I wanted to have a conversation and see how that would go. And I thought, you know, if I had encountered that guy 30 minutes earlier, that would have destroyed my graduate career, and I'd be doing something completely different. So the reason I'm here is because I had a fit of guilt and was nice to that particular person.
I don't know how we're going to top that tonight. So, all right. I know from my time, my 4 years here at the GI, that the two of you have worked together a long time as a team. Talk a little bit about that and kind of what you all do together.
Yeah, so I started at UAF in 2016 and immediately went to Mark's office and was like, how can I work with you? Because I knew he did a lot of interesting stuff, and I knew also that I could travel if I worked with Mark. And really what our working relationship is Mark comes up with all the ideas, and then I work on executing those ideas. I also play a little bit of managerial, Mark, you forgot to do this kind of task, or Mark, check this email, and yeah, it's quite fun. Maybe you can expand a little bit more.
Well, you know, just to go back to my experience as a student, you know, my advisor, who was a the classic gentleman scientist from bygone era. He would talk to the technicians in the department and talk to the students, and he sent quite a number of students to Antarctica to pursue space physics research, and I got an opportunity as part of that. And something that's really satisfying to me now is that I have an opportunity to return the favour and send students like Kylee and others to Antarctica and Svalbard and Norway and all these fun places that we do research in. There's Kylee at the South Pole. So as Kylee said, I write the proposals and come up with the ideas, but Kylee and the machine shop and other people in the department, the ones that actually do the work and make it happen.
I've heard Mark a few times explain what condition his projects would be in without Kylee. So
I think smouldering ruin is the term I use for that.
Kylee, you touched on some of the travel a little bit. Tell us a little bit more about that. I know you've been traveling lately too.
Yeah, I was gonna say, do you want the travel from this year or from all time?
Well, I don't think we have time for all time. So just maybe hit some highlights and kind of where you've been lately and maybe a memorable trip.
Well, this year I started the year at the South Pole and I got back yesterday. So I've been traveling quite a bit. And I actually left Fairbanks in November. And I think from November until yesterday, I spent like 20 hours or 30 hours in Fairbanks. So quite robust travel there. But we have sites all over Alaska that I've been to for installing instrumentation or helping out with a rocket launch. I've also helped with rocket launches in the lower 48. Out in Scandinavia, and Svalbard's pretty cool. We've got instruments in Scandinavia that I've just got back from installing. Antarctica is a big one, obviously. We go there every year for installing instruments, and I also got to work on the design. So once again, Mark came up with the idea, and then I worked on actually implementing the design and doing the 3D modeling for that. And so it's cool to see that then be printed by our machine shop at UAF, and then installing it myself out in the field too. So
Dale, stick your hand up. He's one of the guys in our machine shop there making it happen. One last thing on travel here. Has Mark made travel plans for you yet for what's coming up? Anything?
Oh, we've got a few trips coming up, but I think the main thing that's coming up is we've got a rocket launch, which will be in late March, early April. And so I think there's travel to prepare for that to places like Eagle and Toolik Lake. And then we've got a number, we're going to have students all over Alaska for this rocket launch. So we'll probably talk about that shortly.
Yeah,
and step into my managerial thing and remind Mark to order lasers too.
I'm trying.
All right, one more sort of thing about the two of you before we move on to some science. But neither of you is from here, from Alaska. So just kind of what brought you here?
Well, for me, I did my graduate study in Australia. One of my thesis examiners was Roger Smith, who was here at the University of Alaska. At the end of my graduate study, I spent a couple of years actually working for a marine science program, oceanography and biology around Antarctica. But I wanted to eventually return to space weather, and so I wrote to Roger, who was up here, and I knew there was observatories and facilities in Alaska for studying the aurora and space weather. And at the time, Roger was involved in a big upgrade to the Poker Flat research range. And so they were able to create a postdoc position for me. And coming here I was coming to the place on Earth where you want to be if you want to study the aurora. So it just made sense.
Pretty similar for me too. I grew up in Chicago, and from there I wanted to go to a more nature-y part of the country, so I went to school in the Upper Peninsula of Michigan. And then once I was there, I saw the aurora for the first time and worked on some optics with advisors there. Liked optics, liked the aurora, wanted to know more about it. So where else do you go in the US to study the aurora other than where it's happening, which is Fairbanks? So that's kind of how I wound up at UAF, and the optics part, working with Mark, and also the nature, and yes.
And I should say, as a student, you would read all these papers, and Fairbanks, Poker Flat, and even College, Alaska appear in the literature, and there's a sort of a culture that connects Alaska to the study of the aurora and the space weather, and work by Akasofu and Chuck Deere and others. So this was the place to be, but just based on my reading of the research.
All right, let's do a little bit of science. All right. So trying to understand space weather, before I came to the GI, again, like 4 years ago, you could probably say, 'cause I like science fiction, books and movies and stuff. What are you laughing at? So you could probably say that maybe I got some of my space weather knowledge, from the movies, and I'm sure that's accurate, right?
Definitely.
A wormhole could be sort of like a tornado or something. So I don't know. How accurate are movies, and what's space weather all about? What's it consist of? That's a lot.
It's interesting you mentioned wormholes. I was telling Kylie I saw a cartoon the other day where a scientist is coming out of the lab and a reporter yells out to the scientist, so you study wormholes, right? And the scientist says, yes. And the reporter says, so you've looked into a wormhole. What did you see? And the scientist said, well, I saw a worm. I study insects that infest fruit. Wormholes are not generally what we would think of as space weather. In fact, wormholes are just a theoretical prediction from general relativity. As I think we might talk about shortly, space weather is more the conditions in interplanetary, or the space weather that we worry about is conditions in interplanetary space that are basically driven by events on the sun, and how those conditions, how the eruptions and disruptions that occur on the sun propagate out through the solar system and impact Earth and other planets. We'll probably talk about that shortly. As for how accurate the science fiction is, it's like all things. Some of the stories are well done. Like I think we were talking earlier about The Martian. I think there's some quite good science in that. Others are pretty far-fetched, and it just, it varies.
Anybody see the Martian movie or read the book? Yeah. So that was fairly accurate, right? That's the wrong phrase, but you were telling me there's some bits about it.
It's like a lot of these things. The individual pieces might be scientifically accurate, but then they string together a whole bunch of things that coincidentally worked out just right, and that never happens in the real world. So,
All right, space weather. Okay, it's more than just the solar wind. We were talking yesterday about really what it consists of. So maybe you could tell me the bits and pieces of space weather. Tell us that.
Take that one, Carl.
Yeah, sure. So it is consistent of the solar wind. The sun is constantly spitting out the solar wind, and that's coming towards Earth and also in other directions. Part of that is also the magnetic field. So our Earth has its own magnetic field, but the sun and solar wind has a magnetic field that travels with it. And then I'm going to throw it to you because I think the third part is your favorite thing, which...
So, there's the solar wind, there's a magnetic field, but then when there's a big flare on the sun, it will emit high-energy particles, mostly protons, but also some light nuclei, that are traveling at almost the speed of light, well, maybe 50% of the speed of light, and I call them killer protons, because these are particles that, if you were an astronaut en route to the moon or en route to Mars, or even standing on the surface of Mars when the sun emitted one of these bursts of radiation, the biggest of them would result in death of an unprotected astronaut, I think, within hours or days if they were exposed to one of these big events. So during Apollo, had there been a large flare on the sun when the astronauts were on the surface of the moon, for the biggest flares we see, they might not have come back alive. Apollo was a fairly short, week or 10 days or something program. You can forecast in advance when that might happen. But for a trip to Mars, we can't send astronauts all the way to Mars without providing them with some sort of a shelter to protect them from these high-energy particles. Those particles also damage spacecraft and mess up communications, do all sorts of things. But they will cause spacecraft to fail. They will cause astronauts to fail. So that's the third leg of the space weather triad.
That also might be a part where the Martian is maybe not so accurate.
All right, so to recap, we have solar wind particles, magnetic field, and killer
Killer protons.
protons. All right, and each has a separate effect?
Yeah, so the solar wind is just, unfortunately we don't have a video of it, but we can show videos of the sun where you just see this continuous stream of material coming out, and every so often there's a big puff of stuff that's shot out. We call it a coronal mass ejection. That material takes 2 to 3 days to get from the sun to Earth, and when it hits the Earth, it sort of winds up the activity in our ionosphere and magnetosphere, drives current systems, causes the aurora, causes disruptions to power grids, messes up communication, messes up navigation, messes up radar tracking, all sorts of things. So that's the solar wind. The magnetic field is the thing that determines, when the solar wind hits, the magnetic field that's embedded in it determines whether it penetrates into the near-Earth space efficiently or not. There are some geometries where the solar wind can easily connect to Earth and cause great disruptions. If the magnetic field's not favourable for that, the impact will be less. So
the aurora, right? I think we've all heard of that, right? So, and when I run my sled dogs, I've been doing that for a couple of decades, and it's dark, and I see the aurora up there. It just looks like a pretty thing to me. And I don't know if you noticed when they did the introductory slides, it says not a rocket scientist. That would be me, just to be clear. But how does the aurora relate to space weather?
So the aurora is really one of the only forms of space weather that is a visual representation that we can see here. So it is space weather. It's the particles from the sun interacting with our upper atmosphere, and that's basically a visual representation of space weather.
Is it a result of the killer photons, or which of the three legs of it is it?
So not so much. The killer protons actually do produce this...
protons, not photons.
Killer protons, yeah. Right. It produce a diffuse glow that extends sometimes down to quite low latitudes. I think it's called polar glow or something. It's mostly seen at high latitudes, but can extend down to lower latitudes. It's kind of dim and diffuse. The aurora that you see, like in the picture there, that's the result of the solar wind interacting with our magnetic field. And it's the combination of the material in the solar wind and the magnetic field in the solar wind interacting with Earth's magnetic field and causing... The aurora is just a visual manifestation of a much larger structure that extends thousands or tens of thousands of kilometres out into space, and is systems of currents that surround the Earth and impact spacecraft. There are also radiation belts around the Earth, and they can get energized during the large aurora event, and those radiation belts are sort of occupy the space between the killer protons and the normal aurora. It is radiation, but not quite in the same sense as the killer protons.
So, Kylee said that the aurora is the visual manifestation, right, of space weather, but without getting into the kind of destruction or damage or havoc that space weather can cause. I know we'll talk about that, but are there other manifestations of space weather that affect our lives somehow, or is aurora just the main thing?
So space weather, it disrupts communications, it disrupts navigation, it disrupts radar, it induces currents in long distance power lines, and in the early days in telex things. In terms of experiencing the aurora, has anyone here heard sound from the aurora? Anyone? One or two hands go. So that's an interesting, Kylee was saying, well, one of the only ways you personally can experience space weather is by seeing the aurora. But there's been this possibility for decades that somebody might be able to hear sounds that come from the aurora. Scientifically, it's really difficult to explain how that could work, but you'd be a pretty arrogant scientist to say that to exclude the possibility that it happens. So, and there are a few mechanisms. It's very unlikely that there would be sound generated up at the altitude of the aurora at 110 kilometres altitude. It's very unlikely that sound could propagate down through the increasingly thick atmosphere and get all the way to the ground and still be audible. But as I said, the aurora is just one part of a much larger system, and there are other mechanisms that we think by which it's perhaps possible that electromagnetic forcing of the lower atmosphere could produce sound locally down here rather than have sound propagating down. So I don't know, I'm getting off topic, I think. But
summary is, the aurora is probably the biggest way, and it can have smaller impacts, but maybe not noticed by most people.
All right, so you've told us kind of what space weather is, what it consists of. We talked a little bit about the aurora. We know why the two of you are here. Why is Fairbanks a good place to study the aurora?
So Fairbanks is located, as you can see in this image, under what we call the auroral oval, which is where the aurora occurs mostly, unless you're, in May of 2024, I think, and then you get aurora in Texas and not here. But that's a unique case. And the reason it becomes this auroral oval shape is because of the interactions of our bar magnet-like magnetic field on Earth. So here's an image of essentially a simplified version of our magnetic field. It acts like a bar magnet. So we've got those open field lines, as we call, at those polar regions, and that's where those particles can really come into our atmosphere much easier than somewhere where those lines are connecting back to the Earth. So that's why Fairbanks is, and it's the only place in the U.S. that is in that auroral oval.
Mark?
I had a little comment to add to that. There's a couple of people in the audience here I know are actually practicing card-carrying space physicists like the rest of us. And Kylee just used an expression that the space physics people use often, open magnetic field lines, meaning magnetic field lines that go from the Earth and extend way out into space. We teach our undergraduate physics students that there is no such thing as an open magnetic field line. It is a fundamental property of the magnetic field that every magnetic field line eventually comes back and joins up to itself. And there's no magnetic field line that only has one end, that doesn't form a closed loop. So, people sometimes have difficulty understanding science. Part of the problem sometimes is that the terms we use are actually not really well thought out, and that would be an example of where everyone in our field talks about open magnetic field lines, and everybody in our field says there's no such thing as an open magnetic field line. So, we're not good examples of instruction.
All right, so we know that Fairbanks is a great place to study the aurora, and we've got a great facility just north of Fairbanks, about 30 miles up the Stees Highway there, Poker Flat Research Range, owned by the University of Alaska Fairbanks Geophysical Institute and operated under a contract with NASA. So now we can talk about rockets and the aurora. Everybody loves rockets. Why? I can kind of guess why we use rockets, but tell us the benefit of using rockets to study the aurora and kind of why we can't just do things from the ground or from satellites.
Yeah, so the reason why we use rockets is because it's a really complicated region. So we're looking at a place where if you're on the ground or launching a hot air balloon or something like that, high altitude balloon, you can't reach high enough to get to this region. But if you're in space, then the satellites can't orbit at the heights that we're looking at. It would quickly come back down and crash into the ground. So there's this transition region where there's just nothing that can reach it really, other than sending a rocket straight through it and measuring as you go through the region. And I think we have a slide. Yeah, so this is a graph that...
Everybody understand that?
Yeah. So basically what this is showing is two different processes in those dashed and dotted lines. And you can see at the lower altitudes that what's actually happening in the solid line is really following those atmosphere effects when it's at the low altitude. As you go up, there's that transition region. And then once it gets high enough, it's following those space conditions. So that transition region that's also highlighted there is really a complicated region. And that's, again, where ground-based instruments might have trouble reaching, or lower altitude balloons, which are high altitude balloons but low for rockets, might have trouble reaching, and satellites just can't fly that low. So the rockets are really what we use to get into that region. About
what altitude does the aurora usually show?
So the aurora itself, the lower border, the most easily identified altitude portion of the aurora, It can be as low as 95 or even 90 kilometres for extremely energetic particles. More typically, it's around 100 or 110 kilometres in altitude. Anybody looked out and seen an auroral arc across the sky and it comes down and it appears to sort of touch the ground or touch the mountain off in the distance? I think that's mostly an optical illusion. It's just the aurora disappearing over the horizon and the perspective that makes it appear to touch the mountains. It really isn't possible for those particles to get much below 90 kilometres, even in the most energetic times. So, and that region that Kylee was talking about, to be clear, the bottom portion, you see, the solid curve is the motion of the ions in the ionosphere. Below 100 kilometres, the curve that they're following is that of the wind. It's the wind, the atmosphere, the wind in the atmosphere. The ions are moved around by the wind. In the upper portion, the curve that they're following is the movement that they would have if they were being pushed around by electric and magnetic fields formed in space. And you can see that there's that just jump. But, low down, the ionosphere has to move with the atmosphere. Up high, it moves as it would in open space. And you can see the transition region. And that's the height region that as Kylee was saying, a spacecraft at that altitude would fall out of the sky after a couple of orbits because there's too much atmospheric drag. Balloons can't get much above the stratosphere, so you just can't place any sort of measurement device at those altitudes. And the only way to get measurements from within those altitudes is to send it up on a rocket.
I'm just going to share, you can probably, maybe some of you appreciate a struggle I have as a science communicator. You'll notice the scientists like to use the metric system, so I always have to convert kilometers to miles when I write about what they do. So,
60 miles is
there you go.
about
Right.
how high the lower border of the aurora is.
All right, thanks.
What's that in furlongs, right?
No, not furlongs, no. You did, Mark, touch on something about drag on satellites. And kind of, this gets back into some science a little bit about what space weather can do and how it can affect satellites. And why don't you talk a little bit about that, perhaps?
Yeah, so there can be effect on satellites with drag. And a good example of that is what happened to Starlink back in February of 2022. So Starlink was launching a set of rockets, or a set of satellites, and what they do is they launch them into a low orbit to sort of test them, and then eventually they will boost them up to be actually where they're going to orbit long term. And during this event, we had a large storm happen when they were still in the low orbit, and there's always particles coming into our atmosphere, but during this storm, there's a lot more particles coming in, heating the atmosphere and causing expansion, and then that caused more drag on the satellites, and I think it was out of the 49 satellites that they launched, 40 or 38 fell out of the sky because of this storm period, and that's a significant event if you're losing the majority of your rockets.
38 satellites lost as a result of, actually, it wasn't a particularly large storm.
No, it was a pretty average storm.
And so, that really is a very significant impact on, a technological system that many of us here in Alaska use now, Starlink. 38 satellites lost in one event. It's shocking.
We'll talk a little bit more about consequences of space weather in just a sec, but I want to get back to kind of launching rockets and at Poker Flat. And Mark, you've got a project coming up, a mission coming up that Kylee and others are involved in that deals with space weather. Maybe kind of run through that a little bit, what you're trying to find out.
Yeah, so the mission that we have coming up late March, early April, the acronym is AWESOME. I won't tell you what it spells out, but we're studying impacts of the aurora, and in particular, the purpose of this mission is to look at, we know from ground-based data, that when you go outside and you look at the aurora and you'll see this nice quiet arc there, and it gradually sort of moves a bit higher and higher in the sky, and then maybe around midnight it brightens up suddenly and expands and fills the whole sky, and you have this crazy active aurora, colourful things, what my colleague Richard sometimes calls Hollywood aurora, filling the sky. When that happens, there's a lot of energy and a lot of heat being deposited into the atmosphere, and we know from ground-based observations that following that we see big wave-like oscillations in the upper atmosphere at a couple of 100 kilometres altitude. what we want to do is we want to put some rockets into that wave field and actually measure the gradients and the terms in the wave equation that govern the propagation of these waves, and establish a more quantitative connection between the driver of the waves and the response in the atmosphere. So that's the purpose of the mission. We'll be launching 3 rockets from Poker Flat, one of which will go a long way north and impact in the Arctic Ocean. The first two rockets will be rather smaller and just make their measurements closer to the rocket range. These rockets, among other things, will be deploying tracer clouds that we use. It's very difficult to measure the wind at 150 kilometres altitude, and one of the only ways you can do it is to essentially build something like a giant fireworks display that where you send the rocket up and you, by a couple of different processes, you release some sort of vapour that you can see from the ground. And there's a video I think Sarah's going to play here in a minute. One of the things we're doing now is we're actually not just releasing these traces from the rocket itself, but we're actually ejecting a bunch of little sub-payloads out from the rocket. And instead of creating one cloud, we're actually creating a constellation of many clouds. And looking at the differential motion within that constellation, we can start to pull out some of the terms in the wave activity. I guess the video.
Yeah, let's take a pause because it's got some sound on this video here. This is of one of the launches of the
I guess this is the rocket launch video. Is it not playing, Sarah?
There goes the cursor. There we go.
Oh yeah. So this is we were testing these ejectable sub payloads. This is at Poker Flat. You're about to see this thing. There's a little tiny rocket motor that we use to eject the sub payloads to get them to go fast enough from the parent payload, and you can see this thing coming out of that launch tube there. I can tell you that the whole time that this little tiny rocket motor burns is a third of a second. So you're seeing something that's really very, very slowed down, and you're seeing the thing just sort of slowly emerging from its launch tube and spinning. That will travel, well, in the case of our experiment, that sub-payload will travel close to 100 kilometres away from the parent vehicle before it releases its little tracer cloud. And we've got about 20 of these on the rocket, so we'll be releasing a constellation of 20 little tracers and then watching how the wind field sort of distorts and moves that constellation.
Just a science nugget I like is talk about the wind, and because it's not wind like you and I might think.
Well, it is and it isn't. So at the altitudes that we're looking at, the atmosphere is of course much more tenuous than it is down at the ground here, and you sort of tell people there might be I can't remember 10 to the 15 particles per cubic metre up there, something like that. That's an awful lot of particles, but each one of those particles gets to travel tens of kilometres before it bumps into one of its comrades up there. Whereas in the room here, the air molecules get to travel about 10 nanometres. That's 1/100th of a millionth of a metre. They're banging into each other all the time. At the altitudes we're talking about, these particles will travel tens of kilometres, but nevertheless, there's so many of them that their average behaviour is still behave like a fluid, and there is still a meaningful wind, and there's pressure gradients and all the sorts of things that you think of as the wind. Anyone want to guess how fast the wind blows up there? Faster or slower than on the ground? The answer is it's quite a bit faster. It's typical wind speed might be like 400 or 500 knots versus that would be. Maybe that would be on an active-ish day. 200 to 500 knots, something like that, would be the typical wind speeds that we measure. Pretty quick.
I have to convert that to miles per hour. So.
I think of knots because of my time as doing oceanography. But I was saying to Rod a few days ago, the atmosphere is really tenuous. So even though you might be exposed to 300 knots of wind, if you stood on a giant tower that was 200 kilometres high and exposed yourself to the wind, you wouldn't get pushed off because the atmosphere is so thin that it's moving fast, but there's not a lot of momentum there.
One other thing that might be good for folks to know about that mission is the ground observations and kind of how that works and the locations and who's involved with that.
That's a Kylee question.
So when they have these tracer clouds, you have to image them to see how they move. So what we'll do is we'll have ground sites, and that's another reason why Poker is such a good facility for rocket launching is because we can have ground sites under it, whereas a lot of these places where we can launch rockets, they're launching over the ocean, and it's hard to have ground-based observations on the ocean. But when you have these ground sites, you'll have cameras set up at each ground site that'll image this cloud and over the period of time track how it moves using the background stars. If you do that from multiple look directions, then you can see exactly in 3 dimensions how the winds are changing. So during Mark's launch, we'll have, I think, at least 4 ground sites with cameras that will take images of these clouds and do exactly that. We'll get the images, and later on we'll process them, see how the clouds are moving, and know what the winds are doing.
So this is going to be a big effort involving many people out in the field, communicating back to Poker Flat and telling us what conditions are like, whether it's clear, whether it's cloudy, what the aurora is doing. And we will be essentially occupying a large portion of the northern part of the state of Alaska with camera sites to record these events. So it's a big undertaking.
So one more thing about the rocket discussion here before we get on to the consequences of space weather and how it can affect us directly. Launching a rocket is probably pretty easy, right? So,
well, if you talk about pushing the button, then yes, but
that's Mark's job, right?
Kind of.
No, it's actually not my job. I'm not allowed anywhere near any of that sort of stuff. My job is we have contractors that build the rocket and provide all of the safety and, trajectory predictions and telemetry and all of the aspects that NASA has contractors who do that. The contractors are tasked with executing the mission. My job, I'm their customer. And so when we are preparing to launch, I will request that the contractors perform the launch. And I get to say when I want to launch, but I don't get to touch any of the explosive-y things.
So what's actually, take us into the room there in the Science Operations Center at Poker when, all right, you've got favorable conditions, all right, and you're thinking tonight might be the night, things are looking good. What's it like in those last maybe 2 hours, What's going on in there and at the ground station?
It varies from mission to mission, but every time a launch team comes to Poker Flat with a mission, there's maybe typically, I guess, 50 people or something like that involved in the launch, maybe more, depending how complex it is. Many of those people have spent a couple of years working on it. The rocket flight itself will probably last somewhere between 10 and 20 minutes. And so the science team that are involved in that, they've got 10 or 20 minutes to make the measurements that they've just spent several years working on, and they've got, as I said, this huge team of people supporting them. It's a big undertaking. So it's quite stressful. Choosing when is the right moment to press that button. And it depends on the particular science objectives. In the case of my mission coming up in a month's time, the timing is not particularly critical. I'm not trying to hit the aurora doing some particular thing, but I've seen science teams there where they're actually trying to, it takes 15 minutes for their rocket to fly, and they're trying to predict 15 minutes in the future, the aurora will be in just the right spot for me to make the measurements I want to make. And that's a really stressful call for those people. Fortunately for me, once the conditions, once we've had an auroral event, everything after that is given. So I just wait for the aurora to get active and then I say, all right, we'll go. So it's a lot simpler for me. But we do sit around and wait for a long time. And there are things that can stop you from going. I had a mission in Norway a couple of years ago where the window opened, we had perfect conditions and we wanted to launch, but there was a fishing boat in the hazardous area. And we had, 15 minutes left in the window, and the NASA's on the radio saying, pedal to the metal, see if this fishing boat would actually get out of the hazard area in time. And they just did, with really a couple of minutes left in the window, and we were able to launch. But, that's quite stressful, just wondering whether the grumpy Norwegian fisherman who's not really interested in filling up his nets and going can be talked out of, leaving the hazard area so we can do our experiment.
At the field sites, it's a lot less stressful. We're mostly waiting around and just telling Mark, hey, the skies are clear, or the skies are not clear. We don't have to make a lot of the decisions. We leave that up to him. So
you say that, but there is, for the people who operate those cameras, there's a lot of responsibility because, I have done this myself. I have set up cameras to image a rocket mission in a place where it was quite humid and there was condensation appearing on the lenses. So we had lens caps on the cameras, and I have forgotten to take the lens cap off. And so
we now have a checklist where the last step is take the lens cap off.
You would think this would be a disaster because, the whole purpose of the mission was to photograph these releases, and I didn't take the lens cap off, at least on one camera. That was the bad news. The good news was the rocket blew up before it released its things anyway, so I didn't actually miss out on anything. But
All right, let's turn to what space weather, what it can do to us and our devices and stuff. I mean, when I read my sci-fi books and watch sci-fi movies, it's my cell phone's going to burn up in my hand, right? So what'll it do in a practical sense, potentially, in a real serious event?
Probably to the everyday person, you wouldn't notice too many effects. Like we talked about before, Starlink had their issues with launching satellites, so it can have an effect like that, which then can later affect you if you're, relying on Starlink for internet and all their satellites just went down. It's not ideal. It can also have effect on GPS signals, but again, not necessarily if you're looking at, am I in Alaska or am I in Canada? It's usually not going to affect it that much, but there are things like snowplows who can plow the roads based on their GPS location, and depending on what the ionosphere is doing, the way that the GPS works is it's sending a signal to a satellite and it's relying on the time that it takes to get to the satellite. That's how it's figuring out where it's at in space. It's going through the ionosphere. If the ionosphere is changing, that'll affect the time that that takes, and then your location will be slightly off based on what's going on in space. And if you're deciding if you're on the road or not on the road, you're kind of going to want to know that pretty precise. Can also affect radio signals. So communications rely on reflections off the ionosphere. And again, if the ionosphere is changing, the location of those reflections will change, and then that can affect your communications. But cell phones are communicating with ground towers. So those, and they also are at higher frequencies, which are not as affected by the ionosphere. So typically, you'll be okay.
So my biggest concern then, because I have Starlink, I live out in Two Rivers on the edge of internet land. Any Starlink users in here? Yeah, I see a couple of hands. So, all right, so I'll be able to use my phone, but I won't be able to stream.
The space weather is not going to impact the operating Starlink satellites too much. It did, as we said, it caused a whole bunch of them to fall out of the sky, but that was because they were in the process of being deployed. So once they're up there, they should be fine. But there are other impacts as well. Here in Alaska, we have military surveillance radar systems that rely on radio waves propagating through the ionosphere. And if you see some target on a radar, you'd like to know where it is. Mm-hmm. Well, those radio waves, the path they take through the ionosphere can be significantly changed by the space weather conditions. So, if you think there's a target over there, but it's actually over there because your radio wave is traveling on the wrong path, that will affect your ability to track things with radar. Coming back to your favourite topic, right, of killer protons, if there's a large flare on the sun sending out streams of killer protons, passengers on an aircraft that flew across the pole at the normal 35, 40,000 foot altitude that a transpolar flight would be on, if one of those events occurred when you were up at that altitude and you flew across the pole, the radiation exposure you would get on an aircraft is comparable to several chest x-rays, I think is the figure they give. So those transpolar flights will descend, maybe down to half the normal altitude, just to put more air between them and space so that the passengers are not exposed to so much radiation. So that would be another effect. A problem that we have now is electric currents induced into power distribution grids. It can cause blackouts, and there have been historical instances of that. So you personally, apart from seeing the aurora, you're probably not going to notice that space weather is disturbed, but the technological systems that you depend on absolutely will in the case of a large event.
Now, does it actually damage an electronic system or just disrupt it?
The killer protons can take out. So the sorts of things they can do is they can corrupt computer memory. So if you've got a spacecraft that's trying to figure out where to point its antenna dish and the program gets messed up because the computer memory is corrupted and the dish points in the wrong direction, now you can't talk to it, and it starts tumbling uncontrolled through space and you lose it. And those sorts of scenarios have happened.
A lot of military bases in Alaska, so makes me want to know how does it affect our military? You know, we've got Wainwright, Eielson, we've got the Space Force base down at Clear, and I think the Geophysical Institute does some work with the DoD. But how are they affected? Are they?
They are. There's a few. So when I first came to Alaska about 30 years ago, we had some programs with the military where they were working on projects related to the original Ronald Reagan Star Wars program, where they were trying to come up with missile detection systems. And one of the things that they were interested in there is, you know, you can have a satellite in space that's looking for incoming missiles. It has to be able to identify that hostile target against all the backgrounds, what they call geophysical backgrounds. So it would be, you know, clouds in the atmosphere and lightning. And one of the backgrounds that could confuse their target identification algorithms were active aurora. So we were performing studies to help them understand how they could characterize the aurora as something that would confuse the target identifying capability. Also, for long-range radar, and particularly over-the-horizon radar, where the signal has to bounce off the ionosphere, conditions in space where they significantly disrupt your ability to track targets, particularly in the over-the-horizon case, I think.
You know, something we haven't touched on tonight about the intensity of space weather. We're in solar max right now. So what does that tell us about solar max and kind of what that means for space weather and the killer protons?
The sun goes through solar cycles where it's an 11-year period where, you know, you have solar maximum and solar minimum, which you've probably heard those terms. But solar maximum just means that the sun is more active now. We're seeing more sunspots, more flares. We'll get more coronal mass ejections coming towards Earth, and
more killer protons.
More killer protons, yes, very exciting. So we're in that period right now, which is why we're seeing things like aurora down in Texas. We've seen that, I think, twice last year, and we'll probably continue to see events like that. And then after a few years, it'll start to die down again. It's actually caused by the rotation of the sun's rotates at different speeds, whereas we rotate all at the same speed. Our magnetic field stays nice and uniform and pretty, whereas the sun gets really complicated and therefore creates these holes where the particles can come out more often. So yeah, that's kind of what solar maximum is and why it's affecting us right now.
So what's the difference between a solar flare and a CME, and do they do different things with space weather? Do they cause different things?
So it's the couple of different sides of the same coin. What happens is on the surface of the sun, you get these regions where the magnetic field gets highly contorted and twisted, and that stores a bunch of energy. And all of a sudden, it will sort of release and settle down to a more smooth magnetic distribution. That releases massive amounts of energy. When you've got magnetic fields as strong as the magnetic fields on the sun over regions as large as the magnetic fields on the sun, when the magnetic field sort of essentially settles down into a lower energy state, it releases a lot of energy, and so you'll see a flash of light from that region. Even at visible light, observers looking at the sun will see a little bit of a flash there. Well, when I say a flash, it might last 10 minutes, but you know, it's a brightening. And at short wavelengths, at ultraviolet and X-ray wavelengths that affect Earth's upper atmosphere, it's a dramatic increase of brightness in the sun. That's what we call the flare. And so you have light, radio waves, basically electromagnetic radiation coming from the sun immediately as a result of that flare. But as that happens, the magnetic fields are rearranging, and that sort of causes the sun to spit out a big cloud of material. And it's the cloud of material coming from the sun that produces what you're calling the CME. That's an abbreviation for coronal mass ejection. And then as that, it's the coronal mass ejection propagating out that accelerates the killer protons. So, you know, there's sort of three elements to it. There's the flash of electromagnetic radiation, which gets here in 8 minutes. There's these relativistic protons that get here in about 20 minutes. And then the burst of material that has to then travel from the sun to the Earth to cause our aurora and magnetic storms, that takes maybe 2 to 3 days, depending on the speed of the CME. So there's really those three elements that come from but they're all driven by the flare in the first place, the restructuring of the magnetic field.
All right, I want to turn now to kind of our final kind of topic area here, all right, and that's the future of space weather research. I guess the place to start is there seems to be a lot of interest in it now, heightened interest. Maybe can you tell me kind of why we need to know more about space weather now?
Yeah, we're kind of moving towards a lot of space-based assets with, Starlink giving internet to these rural areas, especially in Alaska, and a lot of other communications are going space-based, and they're talking about, traveling to Mars and stuff. So obviously, if you're going to do stuff in space, you care about what's happening in space. That's a big reason why, there's a big push in the future for understanding space more.
And the commercial operators are figuring out how to launch payloads for dramatically less cost. We're also figuring out how to provide the same sort of functionality in much smaller little spacecraft, maybe the size of a loaf of bread instead of something the size of a microbus or a minivan or something. So the spacecraft are getting cheaper to launch, cheaper to operate, and the demand for them is increasing. So our sort of use of the orbital region around Earth is increasing exponentially. That's an overused word, but it really is true in this case that the amount of stuff that's out there is growing rapidly, and so all of that stuff is impacted by space weather. And here in Alaska, we depend a lot on those sort of assets for our to be part of the connected economy and to be connected to the rest of the world. So we are in a place where the impact on those assets will be felt. So.
To go along with that, the more stuff you put in space, the more stuff you have to avoid in space. Mm-hmm. So understanding how these parameters are going to affect your spacecraft and how it moves and, the drag as to where it's going to push it, knowing where your spacecraft is going to go is very important when there's a lot of stuff up there.
All right, so now let's talk about another project that Mark has going on, and that'll complement a European project, as I understand it, and it also is probably going to put Kylee in the Alaska Airlines Million Mile Club. So
MVP gold right now.
Oh, all right, okay. So Mark, tell us about that and kind of what Kylie's, well, you can talk about your role in it, but you're keeping her pretty busy with it.
So the Europeans are building a big next generation ionospheric radar system that's using what we call phased array techniques to image the ionosphere with really super high resolution 3D volume images of many parameters in the ionosphere. But their radar only looks at the electrically charged ionosphere. It doesn't look at the neutral atmosphere that the ionosphere sits in. And for every one ion that's in the ionosphere, there's about 1,000 neutral atoms around there. So the neutral atmosphere is a much bigger part of the fluid that's up there than the ionosphere itself. So we have sent these three, there's a picture there. We got a local company called Summit Logistics to fit out these shipping containers as human occupiable labs. We sent 3 of them to Scandinavia to be deployed around the region where this new high-tech radar will be operating. And we put instruments, Kylee, on the roof of one of these containers in Sweden. We put instruments in there that will measure wind and temperature and auroral activity and magnetic activity that will sort of collaborate with the big European radar to give a synergistic view of both the atmosphere and the ionosphere working together as space weather disrupts it. So that's the project.
And what countries are they in?
There's 2 in Finland and 1 in Sweden.
And Kylee, you've been to all those places many times?
Yeah. Last year I went out with someone from Battelle, the company that we're partnering with on this project, and we actually installed the containers themselves. So hooking up power, hooking up internet, making sure the heaters are going, making sure we aren't tripping breakers every time we plug something in, which was a problem at one site, making sure the UPSs are going. We did all of that, and then once that was done, I got to go back out and install actually the instrumentation. So I've been to all 3 sites multiple times.
I think it was from Mark recently, you had to chase a delivery truck.
I did, yes. So that was actually like 2 weeks ago.
Yeah, tell us about that. What'd you do?
Yeah, for some reason we have issues with shipping Edelon controllers because this is not the first time I've had to chase one down. But basically, we tried to send it from the group that was fixing it out to our site in Scandinavia, and it was supposed to go to Finland. It went to Norway. It went to Belgium. It went to Denmark, Netherlands, Germany, France, Great Britain. It was all over the place. Eventually, it got to Finland, but then wasn't sure where it was in Finland. Had to call FedEx. Had to call partner companies. Eventually, they said there's this driver who's got it. It spent the night before I chased it down in the same town that I was in, but no one delivered it, of course. So then they told me, oh, the driver's going to this town, and it's about an hour away from you. So if you drive south an hour, the driver will be driving that same way. You can go find him. So I sat at this little restaurant, hotel, gas station in the middle of nowhere, Finland, for 30 minutes. And then finally this giant truck pulled into the parking lot, and I thought, that's for me. Walked up to it. The guy said no words to me, pulled this box out of the back of it, handed it to me, and walked away. I was like, I guess this is it. So,
Sounds very suspicious, doesn't it?
It did, yeah. No name asking, is this yours or who are you? Just,
all right.
Here it is.
So these two projects, the one that Mark is leading and that you chase down trucks for, and the European one, really what's that going to tell us about space weather? Kind of, what's it going to do for us? What's it going to tell us?
There's two real areas of interest in the moment in our field. One is to look at how things happening on the sort of smaller scale, the microphysics, the really detailed coupling between the ions and the neutrals are happening. And so both the European radar and our instruments are designed to zoom in and really look at the microphysics probably isn't the right term, but the much smaller scale aspects of space weather than we've been able to look at in the past, because now we've got these high resolution instruments. But the other part of the story is, if you remember that transition slide I showed you where, below 100 kilometres we've got the normal atmosphere, above 150 kilometres it starts to look like space. In the region where the aurora is occurring, in that 100 to 150 kilometre height range, what goes on is sort of a battle between things like weather systems and jet streams and hurricanes perturbing the atmosphere. So there's all this forcing coming up from the lower atmosphere that wants to disrupt the height range that we're interested in. But at the same token, there's stuff coming from the sun. There's space weather originating from above that's wanting to modify that region. And so understanding how this region where the aurora occurs and where a lot of these space weather effects play out, understanding the sort of balance between what the lower atmosphere would ask it to do and what the space weather would ask it to do, that's kind of where the rubber hits the road at the moment in our field. And this project is designed to, help us understand, how those two processes work together to drive the, day-to-day weather that occurs in that region.
So just a couple more questions here, and then we'll get to audience questions from here and from our online crowd. But you had mentioned Summit Logistics, local company, earlier, and a lot of research dollars come into the university here through NASA, the National Science Foundation. Talk a little bit about kind of Summit Logistics' role.
Yeah, so the project we had in mind was to send these observatories to Scandinavia. You can see that one, if you look on the roof there, you can see there's actually observing domes there. We needed to get shipping containers fitted out to function as portable laboratories. And we sent out bids for tenders across the US actually, and we got quite a number of responses. But I was enormously pleased to discover, I didn't ask for this, but I was enormously pleased to discover that by far the most professional and highly engineered response to our request for proposals we got was from this local company, Summit Logistics, which are just down the road here. And it is so much easier to deal with, building something like this when you can walk down and talk to the people than if you're trying to do it, talk to somebody in Indiana or something and you're in Fairbanks. So that was great. And they were actually just really accommodating for all our needs. They let us store the containers on their lot for 8 or 9 months until we were ready to ship them. no drama about change orders or anything like that. And they came to us with lots of experience, having sent these containers to the North Slope and all across, like similar, facilities all across Alaska. When I said, is this heater going to be big enough? They said, you've got no problem, and we know that because we've actually sent many, many of these out in the field. We're not just telling you our guess, we actually have the experience to tell you that this will work. And so they were great to work with. The other example, I don't know if Sarah's got the picture there, but a few years ago I wanted to test, when we were doing these deployable sub-payloads, I wanted to know whether the rocket motors we're going to use would work in a vacuum. And so I said, I need to do some test burns, fire up the rocket motors in a vacuum and measure the thrust and see if they burn properly. And everybody I knew who had a vacuum chamber said, well, you can't burn a rocket motor in my vacuum chamber because vacuum chambers are pristine, clean, high-tech things, and I wanted to do this, terrible rocket motor experiment there. So we ended up buying a Greer fuel tank and we put a door in the end there and some cable entry ports and things, and we made our own. We called it the rough service vacuum chamber. I think Dale helped build it, and we were able to do these, messy, awful experiments in the vacuum in there, rather than in a high-tech, beautiful, pristine research vacuum chamber. And so again, just working with a local company, we were able to, so we're able to get what we needed, but we're also able to, put a few dollars into the local economy.
And you may not know that we have a pretty extensive machine shop at the Geophysical Institute, and they, Mark draws something on a napkin, as I understand it, and then Kylee does the computer schematics, and then the machine shop prints it. So they make our science instruments. Let's talk a little bit about what the shop does.
Well, obviously, before I do that, if you look at the video there, you can actually, this is a video taken inside that tank of a rocket motor burning, and you can see the writing in the background that says Greer tank on the inside of it, just written in chalk there. So it really is just an old fuel tank. Sorry, remind me.
Machine shop.
Machine shop.
Yeah. It's been really great to work with them because, again, they're local. They're right there, so we can go downstairs and say, "Hey, we want this," or "We want this," and they usually. I think there's a plaque somewhere in the GI that says, their whole job is making the impossible possible, and they do seem to do that for us quite often. But yeah, they've been 3D printing a lot of stuff. They've got a lot of 3D printers there, and they've also, it was helpful again to have Summit Logistics involved as the container makers, because we were able to go over there with the machine shop and see what we're actually putting the things that they're building on, and then they can get a better idea of what's going on. Having everything local is just super nice.
Yeah, and very specifically, if I was to contract that work out to some shop, everything would have to be determined up front, and specified exactly what they're going to do. Whereas having the shop as part of our operation, I can go down there and as you say, like literally draw something on a napkin, and they will turn, and they will make suggestions. Well, maybe it'll be easier to manufacture if we do it this way, and this machine can. We can use this machine, but you'll have to change it a little bit so the machine can do that part. So it's a much more of a two-way process than if you are trying to just send work out, predefined work out to an external contractor.
So for both of you, what's exciting now about studying space weather, and what are some of the challenges? So
I think, for me, one of the most exciting things is this Scandinavian project. The United States just, in the last couple of years, did what they call a decadal survey, a 10-year survey of what the big problems in space physics are. And one of the major recommendations, this is a National Academy of Sciences report, and one of their major recommendations is that, 150 years ago, we had better observations of weather down at ground level than the facilities we have now to observe and characterise what's happening up in the space weather regime. So our capability now is worse than it was for looking at tropospheric weather 150 years ago. So they recommended that we need to establish a network of observatories that can monitor and characterise space weather. And so I think they're really looking at deploying a number of observatories really similar to what we've just sent to Scandinavia. So it's very exciting to think that the work here in Alaska might, be adopted on a much larger scale to send observatories across North and South America to build a national and international capability to monitor space weather much more completely than we can do now.
Kylie, what do you find exciting other than the travel?
Oh man, I was going to say the travel. But yeah, travel is like the biggest part for me. And it's not just me that gets to travel. It's actually, with Mark's launch coming up, a lot of students will get to travel. Our team is a team of 2, but we have a lot of projects going on that require travel. So we've sent other students to Antarctica with me. And now with this next rocket launch, there will be probably 8 students that get to go into the field, and even some undergrads that'll be going into the field as well. And that's a really cool opportunity that Mark's giving to a lot of students.
Just building on that, what about high school students? Is this, is space weather going to be an area of research for a long time?
Yeah, like we said before, we're really expanding our assets into space, so there should be a lot of jobs and, want to understand space a lot more, which will be a good career path for a lot of people.
Not to mention that of course, every science nerd in the high school would like to work on rocket experiments or, go off to fun places to study the aurora. So it's a really fun job. As Kylie said, with the big expansion of space assets, there's going to be lots of career opportunities. And when I was a high school student, I imagined my career path I wanted to have was to be an astronomer. And then about the time I was completing my undergraduate studies, I thought, well, astronomers might study some distant galaxy, and that's interesting, but it's not going to impact society very much. But if I could come to a little bit closer to Earth and study the space weather around Earth, I would not only be doing some fun stuff, but I would be studying something that would actually have an impact. And so that would be the other thing I would tell high school students is this is a field where the work you do matters, and there's probably going to be lots of work to be done.
All right, last question here from me, and then we'll turn it over to the audience here. What do you want the audience to take away tonight from this? What's the main thing you want them to know?
Go first.
About space weather.
So my take, you like to read science fiction, right? So science fiction is becoming science fact now that we're actually looking to expand, send humans back to the moon, perhaps send colonists to Mars soon. All those explorers leaving Earth will have to deal with the space weather that they will be exposed to on the way. And in particular, as I said, astronauts going to Mars are going to have to worry about kiloprotons, and astronauts standing on the surface of Mars are going to have to worry about kiloprotons. So maybe the thing that I'd like people to get from this is that we're entering an era where humanity is starting to occupy space in a way that we haven't before. At the moment, mostly with robotic spacecraft, but shortly with more astronauts. And the space weather we study will really matter to our ability to, if we want to expand our footprint beyond just the Earth and move out into the solar system, we're going to have to deal with space weather.
I think probably my biggest takeaway is that, space weather is accessible to, especially everyone in this room, with being somewhere where you can see the aurora, and that is space weather. But also, for people in the lower 48, this is really a time when it's probably going to be possible to see aurora from down there. And, we're just people too. So definitely feel free to ask us questions and, reach out. And if you want to learn more, it's not that hard to do a little bit of research and learn more about this.
All right, thank you both very much. Let's hear it for our guests. All right. And where's Sarah?
Behind you.
I'm right here.
Okay, back to you.
Thank you. Rod, do you want to sacrifice your microphone for questions, or should we just use the one?
I can be a microphone runner.
That'd be great.
Okay, because I've been sitting.
All right. Okay, any questions from the audience for Mark and Kylie? From the in-person audience, we'll start there. Just raise your hand and we'll bring you a mic. Looks like there's one far back, Rod.
Question there, I think.
Okay, where am I going? Up here? Okay.
No questions for you, Tony.
Similar. So I just had a question, before I get to, I just had a question, was it a little hobbyist Estes type rocket that we used to eject those subpayloads? The answer is close. It was a sort of a high-end hobbyist rocket motor, really well engineered, but something you can buy for $50 or something like that. And we can buy them off the shelf cheaply, and they're extraordinarily powerful. You could really hurt yourself with one of those things.
All right, I got one over here.
a non-science question. Kylee, from what I understand, you're a unicorn, a female physicist. Can you talk about any milestones that you've seen in terms of women in science?
Yeah, so that is kind of true. And it's unfortunate, but yes, there has been. I mean, at UAF too, I feel like we've seen more females coming into the program in faculty and in students. But yeah, there are a lot of years where it's all males. And there are some times when, my advisor or other people send me into the field by myself and say, are you sure you want to do this? Like, are you comfortable with this? And I appreciate that from them, but it is unfortunate that it's still something that we have to think about. In terms of milestones, I mean, for me, just having the confidence to go into the field and know that I'm going to be sent somewhere where I'm essentially in charge of a bunch of men and having the confidence to be able to do that is, I've now established that I can do that, and that's a personal milestone for me. So, thanks.
Any other questions in our in-person audience? Looks like Doa has one right in front of you, Rod.
Thank you. Thank you, Kylee, and thank you, Mark. I want to ask about the future of space weather in Alaska in terms of infrastructure, and as a topic very dear to my heart in terms of geomagnetically induced currents. Do you expect any future infrastructure damage? Can you talk a little bit about that as we are expanding in the East-West?
So was the question, I didn't quite hear, did you ask about damage to infrastructure or expansion of
ground infrastructure.
Damage?
Expansion. Expansion.
Oh, expansion. So, we have a number of world-class facilities in Alaska already. We have the Poker Flat Research Range. We have the HARP facility down at Kokona, and we haven't spoken about that, but HARP is really cool because I always say to people that, the standard practice for a scientist when you see someone put something in front of you and you're not quite sure what it is or how it works, well, the first thing to find out something about it is you just hit it with a whacking great hammer and see what happens. And that's pretty much what HARP does to the ionosphere. We're actively perturbing it to see how it responds. And so I think there's ongoing development of facilities there. There's a big new LiDAR facility being developed for that. I think there's citizen science initiatives deploying small instruments across Alaska for space weather monitoring. And some of the instruments that we've been sending to Scandinavia, we have similar ones in Alaska that we're operating and upgrading. I don't think there's a major upgrade in place, but we've got major facilities that we expect to continue to operate. Does that answer the question? Or?
Right, I have another one here.
So when you talked about the killer protons out there and the astronauts going to the moon and to Mars, what kind of shelter were you kind of talking about? What would it take to actually protect the astronauts out there? Lead obviously is very heavy, probably very expensive to put into space, so I don't see that. But do you have any other suggestions of what you would recommend?
So my understanding is that the whole game is to try and design your spacecraft so the stuff that you need to send anyway, so shielding yourself from killer protons, it's just a matter of putting as much mass as you can between you and space. And so one of the solutions people have talked about is if you're on a long-duration spaceflight mission to Mars, the spacecraft will have to store a reasonable amount of fresh water for the astronauts to use. So maybe you can build your water tank such that there's a hollow in the middle, and you can put the water between you and space. So that would be one possibility. But also other, trying to arrange the more massive parts of the spacecraft to be on the outside so that they can form part of the shielding. So as you say, just flying lead just for the purpose of providing a shield would be expensive and difficult. So there may still need to be some of that done. But the first port of call is just to design the spacecraft so there's a place in the core of it where the astronauts can get. And to be clear, those astronauts might have to stay in that shelter for 2 to 3 days or even longer. So once these flares go off, it's not the flare itself, it's the shock front expanding out from the sun that accelerates the the protons to these, dangerously high energies. And that shock front propagates, well, actually, there have been times when it might even be as long as a week. So if you've got a little tiny shelter the size of a broom closet that you've got to be in for a week, it's probably pretty annoying, but that's going to be part of the job.
All right, we're going to move to some online questions. We had 120 people join us online. Folks from around Alaska and Homer. We had someone from Port Townsend and Washington. We have some favorite sci-fi movies, The Martian, Star Trek, and 2001: A Space Odyssey. So, all right, a couple questions from Christopher on Zoom. Where does the burned out rocket fall back to Earth?
Depends on where you're launching it from. But here in Alaska, the first stage, they break off in stages. So the first stage will come back down actually pretty close to the range. And that's one of the benefits of launching in Alaska, is that we aren't very populated once you get out of town. So you can safely do that and have it crash back down. But then it really depends on, how high is the rocket flying, or how far are you trying to launch it in terms of your angle of the launch as to where it crashes back down. I don't know where yours are crashing back down, the ocean?
I think you basically answered the question that the early motor stages land close to the range. The final motor stages land some distance away, depending on the mission. For my large Black Brown 12 rocket, all of the upper stage and the experimental part will actually land in the Arctic Ocean and not be recovered. For at least major components of the rocket that will come down in Alaska, Poker Flat and NASA have what they call a clean range policy, where they put locator beacons on all the rocket components that are expected to impact, and they go out and recover them. So we're no longer. 30 years ago, we probably would have just left them there, but we're actually actively trying to find old motor stages from the past, and all the new missions going forward have mechanisms built in to make it such that we can recover everything and bring it back as part of this clean range policy that they have.
And Mark, I think it would be good just to point out to people that the range does have sort of a bounty program too.
Oh yeah.
So for local bush pilots and stuff, if they find parts of a rocket, they can send us GPS location, and then they don't even have to, go and pick it up themselves. The range will take the GPS location, and then you win a bounty based on, I think, the size of the part you find. So it's an incentive for the locals to go out and go rocket part hunting, I guess.
That said, sometimes there are souvenir hunters too that would like a piece of a rocket to put on their shed somewhere.
One more question from online. This is from A. When there's a solar flare, does that increase the UV index or sun damage risk on Earth? If so, how long does it last for?
So I'm imagining the questioner is asking about the UV index that you would think of as something that you would worry about for things like sunburn.
Yeah.
I think the answer to that is no. So it turns out if you look at the spectrum of energy of radiation coming from the sun, most of the energy is in the visible wavelength range and out into the near infrared. And the sun is remarkably constant in terms of its brightness over that range. It really doesn't vary much at all. It's a thermonuclear reactor. We can't build something like that's stable in any sense, let alone as stable as the sun is. The sun is just really rock steady. It's a beautiful power source for our solar system. And you have to get down to quite short wavelengths, shorter than the wavelengths that matter for that UV index, before the flares and the variability in the sun start to become significant. So if you go to, less than 200 nanometers wavelength, sure, the brightness goes up and down, and a flare will greatly increase the radiant flux density at those wavelengths. But at the wavelengths that are biologically significant for suntans, the variation is very small, I think.
All right. Well, thank you, everyone, for joining us, and to our online audience. Another hand for Mark and Kylee.